Let's say you have a block of, let's just say this is glass, and then outside of it is air. And if you've got this incoming ray of light, let's say a ray of light coming in, let's make that a bigger angle here. Ray of light coming in like this. This incoming ray of light we usually call the incident ray. So this incident ray is just this ray of light that's coming in towards the surface. And we're going to measure that angle based on what we call the normal line. Normal line, it just means a line perpendicular to the surface between the materials at that location. And so the angle we're going to be talking about is the angle that the incident ray makes with the normal line. So let's say we call that theta 1. So that's the angle of incidence. And when this ray of light hits the surface, what's going to happen to it? What would this light do? Yeah, it's going to both refract and reflect. Refract, meaning some of the light goes through into the glass, and also reflect, meaning some of the light bounces off. And when it reflects, so some of the light bounces off the surface. This would be called the reflected ray, or just the reflection. And what would you expect about this angle that the new reflected ray makes with the normal line? Like if you've got light coming in at some angle with the normal line, what would you expect about the angle that the reflected ray makes with the normal line? Should be the same, yeah. The whole idea of a reflection is that the angle that it's reflected at, the angle of reflection, should be exactly the same. So this is just another copy of theta 1. And this is ultimately a symmetry thing due to the fact that it hasn't actually changed medium. We've got light in air. The reflected ray is still light in air. Since the medium hasn't changed, we shouldn't expect the angle to change either. But the refracted ray, when we go from air to glass, we are changing the medium, and therefore we're changing other properties of the wave. And that, among other things, causes the angle to change. And I've seen a lot of different mnemonics for trying to remember which direction the light goes. Like if you imagine the light just continues in a straight line, if the light did continue in a straight line, it would make another copy of the same angle. But it's not going to go in a straight line. It's going to bend when it changes from one medium to another. If this were also air, if it was just going like from air to more air, there would be no change. But with a change in medium, we also get a change in angle. The light's going to bend. And I've seen, like I said, I've seen a lot of mnemonics for this. Like imagining it as a truck that's driving on pavement and then hits some mud or something. I always find those difficult to remember. So what I usually do is I just look at the speed. Speed of light in air versus speed of light in glass. Does light travel faster in air or in glass? Yeah, light travels faster in air. It's still traveling tremendously fast in glass, but glass does slow it down a little bit. So air allows light to travel fast. Glass causes light to travel a little bit slower. So from air to glass, the speed has decreased. That also means the angle decreases. Whatever happens to the speed, you get the same thing happening to the angle. So if the speed has decreased, then the angle, this angle here, is also going to decrease. So what we're going to expect is the ray of light, instead of going straight through, the ray of light is going to bend to make the angle smaller. So we're going to get a bend. And you could describe that as a bend towards the normal line. But the important thing is it makes the angle smaller. So this new angle, we might call, let's say, theta 2, would be the angle of refraction. And then we would call this ray of light the refracted ray. So the ray of light that bounces off is going to be at the same angle. The reflected ray is the same angle as the original ray. But the refracted ray gets bent, and whatever happens to the speed, the angle also changes in the same way. Not the same amount. It's going to be, that's going to be changing relative to a different equation. But if the speed gets smaller, then the angle gets smaller. If the speed gets bigger, then the angle gets bigger. So that's the core idea of refraction and reflection. Refraction is the amount of light that passes through. Reflection is the light that bounces off. And typically you're going to get some of each. If you've got like a bright beam of light coming in, it's going to split into two dimmer beams of light because some of it goes one way, some of it goes the other way. Any questions on the terminology there so far? And have you seen any equations yet describing how theta 1 and theta 2 are related? How much the angle changes as it passes through? And what equation do we use for that? Yeah, Snell's law is the equation governing how those angles are related, theta 1 and theta 2. Snell's law is relating theta 1, the angle of the incoming ray of light, and theta 2, the angle of the refracted ray of light. We don't have to worry about the reflected ray because we know that's going to be the same angle anyway. But the incoming ray of light angle, again, always measured from the normal line, and the refracted ray of light angle, again, measured from the normal line on the other side, are related based on the sine of both angles multiplied by these constants called the index of refraction. And the index of refraction, n sub whatever, is a property of the material, which you would typically look up on a data table or it would be given in the problem. Like you'd have the index of refraction for air and the index of refraction for glass. And the way that's actually defined is based on the amount that it slows down light. A large index of refraction means it makes light travel much more slowly. Small index of refraction means it allows light to travel fast. So air is going to have a low index of refraction because it's got fast light. Glass has a higher index of refraction because it makes light slow down more. And the way it's formally defined is as a ratio Specifically, it's the speed of light in a vacuum divided by the speed of light in that material. And the speed of light in a vacuum is the usual 300 million, or 3 times 10 to the 8th meters per second. But the nice thing about index of refraction is you don't really have to worry about speed of light in a vacuum versus speed of light in that material. The index of refraction is the ratio of those. So the units cancel out anyway, and you just get a unitless constant, unitless ratio. And of course, that's always going to have to be 1 or greater because the speed of light in that material can never be more than speed of light in a vacuum. So this is always going to be the fastest speed possible divided by some slightly slower speed. So it will always be some ratio a little bit more than 1. For air, air allows light to travel almost at 300 million meters per second. So for air, n rounds off to about 1. For other materials, the index of refraction is going to be some amount greater than 1, maybe 1.3, 1.5, 2, something like that. And the slower it makes light travel, the more it makes light slow down, the higher the index of refraction will be. But those quantities are what determines how much the angle changes. And since this has 4 variables, if you know any 3 of them, you can immediately find the 4th. So for instance, maybe you know the angle it's coming in at, and you know the index of refraction in both materials, then you can solve for theta 2 and figure out the angle it refracts at. Or alternatively, if you can measure both angles, if you're doing an actual physical experiment, sending in this ray of light, measure both of those angles with a protractor, plug those in, and presumably you know N1, because for air, N is just 1. And then N2, N2 you can then calculate by isolating that variable. Any questions on that so far? All right, so that's the basic idea of refraction and reflection. And then mirrors and lenses are just specific applications of that core idea. Yeah, 2 lenses. If we have time, we can get to the 2 lenses. Otherwise, we might do that next time. For now, though, do you want to focus on mirrors or lenses to start with? Because I think today we're probably just going to have time for one or the other, and then we can cover the other one next time. So do you want to start with mirrors or lenses? All right, let's try lenses, and then we can go over mirrors next time if we get to it. But for lenses, lenses is really all about the idea of refraction. A lens is allowing light to pass through the lens, but causing it to bend in a very specific, controlled manner. We're taking advantage of this principle of refraction with a very specific shape, the lens shape itself. For example, if you have a lens that is shaped like this, so a convex shape, if the sides are bulging out. So instead of just flat sides, the sides are bulging out, then this is going to cause light to behave in a very specific way. In particular, let's say we just have a bunch of rays of light coming in parallel to each other. In this diagram, let's say just horizontally. In particular, let's say we have one coming in along what we call the optical axis. This line of symmetry, the optical axis. In that case, at that location, the normal line is the optical axis. So if you just got a ray of light coming in along the normal line, what would you expect to happen to that? If we go back to Snell's law, if this is coming in along the normal line, what's the angle it makes? Oh, and as for reflection, some of the light is going to bounce back, but we're not going to worry about the light that bounces back because the main purpose of a lens is to allow the light to pass through, but bend it as it passes through. So there is some reflection. For instance, if you look at somebody wearing glasses, you can see your reflection in their glasses. But the reflection isn't the important part. The important part is the light that passes through and gets refracted. For a mirror, we would care most about the reflection. For a lens, we care most about the refraction, the light that gets through. But what's the angle between the incoming ray of light and the normal line at this point? Yeah, a 0-degree angle. Sine of 0 is 0, so this whole side is 0. It doesn't matter what n1 is if the sine of 0 is 0. Meaning the other side also has to be 0. The only way for that to work is for theta 2 to also be 0. So this is basically the one situation where refraction doesn't change the direction. If the light's already coming in along the normal line, it's just going to keep going. It's the other side, and it's still parallel to the normal line. So that means on the other side, it just keeps going straight through as well. So a ray of light coming in along the optical axis, hitting the lens in the exact center, is just going to keep going straight through. But let's say we have a ray of light down here that's parallel to the optical axis. This parallel ray coming in hits the lens right here. And if we draw in a new normal line here, normal in the sense of perpendicular to the surface itself, then this ray of light makes this angle, this incident angle with the normal line. And if the ray of light just continued straight through, it would make the same angle with the normal line. But of course, it's not going to continue straight through. It's going to get refracted. And if we assume we're going from air to glass, or maybe transparent plastic, or maybe water or something. So let's say we're going from air to glass. Is the light getting faster or slower during that transition? Yeah, light's getting slower, so that means the angle is going to get smaller. Velocity decreasing means the angle also decreases. So instead of going straight and making this angle, it's going to have to bend to make the angle smaller. So to make the angle smaller, it's specifically going to bend towards the normal line. So bending like this, making a smaller angle. And then the ray of light hits the other side of the lens. So we're going to have to draw in a new normal line. Normal line at this point, again, just a perpendicular to the surface. It's currently making this angle with the normal line. If it continued with no bending, it would just be like this, making the same angle. But since it's going from glass to air, from slow to fast, what has to happen to the angle? Yeah, the angle is going to have to increase. The speed increases, therefore the angle increases. So this ray of light is going to have to bend in order to make this angle bigger. So that'll be a bend away from the normal line. So something like this. And so the overall result is that these two rays that started off parallel to each other, we'd expect they never meet, they bend to converge together, meeting at this one point. And it turns out this is going to be true for any other ray that comes in parallel to the optical axis as well. If you've got a ray of light, let's say up here, coming in parallel to the optical axis, if you do the ray tracing and figure out how it bends at each time it hits the surface, at this surface, it's going to bend to make the angle smaller. Again, we could draw in a normal line at this point. It's going to bend towards the normal line to make the angle get smaller. Instead of continuing in a straight line, it's going to bend to make the angle smaller. And then over here, we draw in a new normal line. It's currently making this angle, but it's going to bend away from the normal line to make the angle bigger. And if you draw this out precisely and measure the angles and everything, you'll find that this ray also intersects the others at the same location. In fact, this will be true of any rays that come in parallel to the original optical axis. This parallel ray is going to bend and bend. This parallel ray is going to bend and bend. All these rays that come in parallel to the original optical axis end up bending to intersect in this one location. And of course, they don't just stop there, they keep going. But that one location is called the focus or focal point of the lens. And the location of that focal point is really the most important single piece of information about that lens. If you know the focal point, you don't really need to worry about what's going on inside the lens. If you know the focal point, you can just say, any rays of light that come in parallel are going to ultimately bend towards the focal point. So the other information about what's going on inside isn't really necessary. If you have a convex lens, we would often call this a converging lens. So the shape of this lens would be called convex. The behavior, what it actually does to light, would be converging. So we would usually describe this as a converging lens. And the way we would draw that, in an actual diagram, we don't usually draw out the full shape of the lens. We just draw it in a simplified way as just a single vertical, well, not necessarily vertical, a single line. Could be in any orientation, with end caps curving inwards. So these inwards curving end caps just mean this is a converging lens. So if you draw out a schematic diagram, usually we just draw a single line for the lens because we don't really care about the shape of the lens. We just care about, we're treating it as essentially just a single flat plane, a thin lens. Because we're treating the thickness of the lens as very, very thin compared to the other distances. But we do want to show that it's a converging lens, so we show that symbolically by drawing these inwards curved end caps. Let's say we have the optical axis, and let's say we know the focal length. That distance from the lens to the focus is called the focal length, or focal distance. And that's generally just written as the variable f. And this is going to be the same on both sides. We're going to have another focal point, the same distance on the other side. Because if you reverse this, if you send in a bunch of rays parallel to each other this way, they're all going to bend to converge on one other point on the other side. And due to symmetry, it should be the same distance on the other side. So a lens is going to have a focal point on both sides, same distance on both sides. So if you send in a ray of light parallel to the optical axis, you know it's going to bend to hit the other focal point. Any ray of light that starts off parallel to the optical axis must bend to go through what we often describe as the far focus. That is the focal point on the other side. Any questions on that so far?
I have a question for the, would we be expected, to be able to just, draw, normal lines and make the rays from those, or do we just, follow the three principal rays?
If you're drawing out a schematic of what's going on with the lens?
Yeah, or I guess whatever other kind of problem they could ask us.
In general, if you already know what type of lens it is and where the focal points are, you don't really need to worry about what's going on inside the lens, because if it's a converging lens, then you know that any ray that starts off parallel is going to bend towards the far focal point. This is what the focal point means. It's the point that all those originally parallel rays bend towards. For instance, all these parallel rays, by actually trying out the ray tracing within the lens, looking at the normal lines and how it bends with Snell's law, all those rays that started parallel bend towards this one point on the other side. So we call that point the focal point. If we're saying this lens has this focal point, what we're saying is any ray that starts parallel is guaranteed to bend towards that focal point. So if you already know where the focal points are, you don't really have to go through the ray tracing inside the lens. You can just jump straight to the conclusion that a ray that starts parallel is going to bend towards the far focal point. And that's true on either side. If we had a ray on this side that starts parallel, it's going to bend towards the far focal point on the other side. Any other questions on that so far? And this is also reversible. I mean, we've been looking at this as a ray that starts parallel is going to bend towards the focal point. But any ray of light, you can travel that path in one direction or the exact same path in the other direction. Any ray of light that starts off through the focal point is going to bend to become parallel. So these rays could have gone this way, and they'd be following the exact same path in reverse. All paths light can take are going to be reversible. So that means if you have a ray of light that starts off passing through the focal point, let's say this ray of light right here, and it doesn't really matter where it starts. Maybe you've got a ray of light from the focal point traveling towards the lens, or from somewhere further back traveling through the focal point to get to the lens, or maybe even it doesn't even go through the focal point. Maybe you've got a ray of light that starts here and goes towards the lens without even passing through the focal point. But as long as it's on the same line that contains the focal point, that counts as good enough. That's a line that's a ray of light that is collinear with the focal point. That guarantees that it's going to bend to become parallel. So any ray of light that starts collinear, that is on the same line as, with the focal point or focus, is going to bend to become parallel. So these are both true. Any ray of light that starts parallel to the central axis is going to bend to become collinear with the far focus. Any ray of light that starts collinear with the near focus is going to bend to become parallel, because light paths are reversible. So these are two very useful rays to draw in, two very useful facts to know about how light bends when it hits a converging lens. And the third one you can draw in, any ray of light that's going straight towards the center, like the exact center of the lens here, is just going to keep going. It might be displaced a little bit, but a very small amount, because we're assuming the walls are, the lens is so thin. So any ray of light going straight towards the center of the lens, you can treat as just continues in a straight line. No displacement or no bending at all. So those are usually called the three principal rays. If you're drawing out rays of light coming from a single point, the ones you want to focus on are the ray of light that starts off parallel and then bends through the far focus. The ray of light that starts off collinear with the near focus, that's going to bend parallel. And a third ray that starts off going towards the exact center of the lens and just keeps going. Any questions on those three types of rays so far? So let's try applying this to an actual ray tracing example. Again, staying with the idea of a convex shaped lens. With an optical axis. And let's say we know where the focal points are already. Let's say we've got a focal point here and the other focal point the exact same distance on the other side. And that distance is going to be called F, the focal length. And for a converging lens, we define focal distance to be positive. If it's a diverging lens, we would use a negative value for the focal length. And that's basically just to get the equations to work. The idea of the thin lens equation that you may have seen already is an equation that's specifically tailored to work for converging lenses. But you can get the same equation to also work for diverging lenses if you treat a diverging lens as having a negative focal length. So in general, the focal length is a positive number for converging lenses and converging mirrors as well. The focal length is a negative value for diverging lenses and diverging mirrors. So that's the general rule we use for choosing the sign, positive or negative, of the focal length. In fact, let's assign a number to that. Let's say the focal length is, let's say, 6 centimeters. And of course, there's one focal point on each side. They're both 6 centimeters away from the lens, because we're going to be measuring all the distances from the surface of the lens itself, or really from the center of the lens, but we're assuming it's infinitely thin. And let's say we have an object. The object is just some physical thing that's emitting light. And it doesn't really have to be creating the light. Maybe you've got this object and light from the sun is bouncing off of the object. But since the light is bouncing off of the object, we can still treat the object itself as where the light is coming from. So let's say you've got just some, I don't know, maybe a lamppost or something over here. And this object is emitting light. We've got light coming out of this object in all directions. And we're also going to describe the location of this object as a distance measured from the lens itself. So the distance from the object to the lens, measured from the lens itself, is going to be called O, the object distance. And let's say we have a value for that too. Let's say this is, let's say 14 centimeters. Yeah, that should work. So let's say the object distance is 14 centimeters and the focal length itself is 6 centimeters. And what we can do is we can use ray tracing to figure out what happens to the light that leaves the object. And again, light's coming from the object outwards in all directions, but we only really need to care about the directions that are going to be easy to draw. For example, we could have a ray of light from the object that starts off parallel to the optical axis. Specifically from the top of the object. It starts parallel to the optical axis. What's going to happen to a ray of light that starts parallel? That's going to bend in what way? Yeah, it's going to bend to go through the focal point. A ray of light that starts parallel bends towards that far focal point, because that's what the focal point means. The focal point is the point that all the originally parallel rays bend towards. So that's one of the, what we usually call the principal rays. Principal rays in the sense of rays that are easy to draw out because they follow these specific rules. What's one of the other principal rays we can draw in? A ray that starts off in what way? Yeah, if we have a ray that starts off collinear with the near focal point, in this case, just from the object going, and again, from the top of the object, going straight through that near focal point, that's going to hit the lens at some point. And since it started off going through or collinear to the near focal point, what's going to happen to it? It's going to bend to become parallel to the optical axis. And then one more ray we can draw in, and note that these alone are enough. These two rays, any two rays are enough to define a single point of intersection. But to make sure it's a good idea to draw in a third ray to verify that they really do all meet at that point. Specifically, a ray of light from the object towards the center, the exact center of the lens, should just keep going straight. And I may have been a little wobbly on the diagram here, but in an actual diagram, to be really precise, you probably want to use a straight edge on a paper. So use a ruler or whatever other straight edge to make sure your lines actually are straight. But it looks like all of these rays, and not just the three rays we drew in, but any ray of light is going to follow this pattern. Rays of light from the object hit the lens and bend, and all approach this one point. And of course, they keep going. Which means if you, as an observer, are standing over here, what you see is not rays of light that seem to be coming from the object. What you see is these final rays of light that, as far as your brain can tell, all seem to be coming from this one point. Ignoring everything else that happened, as far as you can tell, these final rays of light seem to have come from this point. So what do we call that point that all the rays of light seem to be coming from? Yeah, that is the image. This location right here is the image of the object. And the reason we call this the image is it's what it looks like the object is at. If you're standing over here, you're not really seeing the object. The rays of light coming from the object don't directly get to your eyes. The rays of light that get to your eyes are rays that seem to have come from this point. Even though they originated from the object, the last point they seem to be coming from is this point right here. So what you're going to think you see is a copy of the object at this location. But since the original object was above the axis, but this new intersection point is below the axis, you're going to see an upside down copy of the object. So we would say that the image you see is inverted or upside down compared to the original object. Also, since the rays of light actually did pass through that point, we call this a real image. Sometimes you get an image that's just the rays of light seem to be coming from that point, but they never actually pass through it. In this case, these rays of light actually did all pass through this point. So we call this a real image. And then the distance, again, as measured from the lens itself, is called I, the image distance. And the usual rule of thumb we use for positive and negative is the direction light is traveling at the end is the positive direction. For instance, in this case, after interacting with the lens, the final rays of light are traveling to the right. So in this context, we would treat to the right as the positive direction. The direction the final rays of light are traveling. And that's a rule you can use for lenses and mirrors. They might suggest trying to memorize different sets of rules for lenses and for mirrors. But if you keep this in mind, the idea that the positive direction, for the image anyway, is the direction the final rays of light are traveling, that's true for both lenses and mirrors of any type. So you really only need to memorize this one rule, that for images, for the value of I, the positive direction is the direction the final rays of light are traveling. That's how we define the positive direction. So for this real image, since this is on the side of the lens that the rays of light are traveling in the end, we would say I is a positive value. And we can actually calculate what this will be using the thin lens equation. And what is that equation? The equation that links image distance, object distance, and focal length together. Have you seen a formula, an equation for that yet? And what is that equation? Yeah, 1 over the object distance plus 1 over the image distance equals 1 over the focal distance. And since we have two of those, we know the object distance, we know the focal length of the lens, we can plug those in and solve for the image distance. And you could do that by plugging in the numbers first and then isolating I. But the thing is, we're probably going to be needing to solve for I lots of times. There's lots of situations where you know the focal length of the lens or mirror, and you know where you put the object, and you want to know where is the image going to appear, where does it seem to be. So let's preemptively solve for I before we even plug in any numbers. How would you isolate I in this equation? How could you get I by itself there? Yeah, subtract 1 over O from both sides. And then what? Yeah, we'd have to invert. The only problem is if you invert both sides, 1 over I inverted becomes I. But this whole thing inverted becomes 1 over F minus 1 over O. which works, but it's really inconvenient to deal with fractions within fractions. So generally in a case like this, what you want to do is combine these into one fraction first. In this case, we could find a common denominator just by multiplying the first one by O over O, multiplying the second one by F over F. So we get O minus F over, and these are now the same denominator, O times F. Now that we've just got a single fraction equals a single fraction, we really can just invert both sides much more easily. 1 over I inverted becomes just I. O minus F over O times F inverted becomes O times F in the numerator over O minus F as the denominator. So we can use this as an alternative way of writing the thin lens equation. This version I find usually easier to remember, 1 over O plus 1 over I equals 1 over F, because it's just inverses added together. But this one is a more useful format if you're going to be solving for the image location over and over and over again. Just solve it once or for all with variables, and then you can plug in numbers as whatever you want. For instance, in this case, we plug in the values O and F. 14 times 6 divided by 14 minus 6, O minus F. 14 minus 6 would be 8. And this ends up being centimeters times centimeters divided by centimeters. One of the centimeters cancels out, so we're left with just centimeters. And we can reduce this. 6 over 8 reduces to 3 over 4. And also 14 and 4 are both even, so that reduces to 7 over 2. So 7 times 3 is 21, divided by 2 is 10.5. So we should expect the image to appear at 10.5 centimeters. Since that's positive, that's in the direction light is traveling. And 10.5 centimeters, let's compare that to the result we got here. That's out to the focal distance plus less than double the focal distance, because double the focal distance would be 12 centimeters. So it looks like our diagram resulted in pretty close to what the equation predicts. I would trust the equation more than the diagram, of course. This is exactly where we should expect the image to appear given these numbers. But drawing out the diagram, even if it's kind of a sloppy diagram without really using straight edges to make it more accurate, still at least gives you a pretty good idea of where the image appears, and perhaps even more importantly, why it appears there. Because these rays of light bend in this way. So these final rays of light, once they hit your eye, seem to be coming from this location. So that's what the image is. Any questions on that so far? Then let's run one more quick example of ray tracing with the exact same lens, but let's just put the object in a different location. Because something very different is going to happen if we put the object closer to the lens, like closer than the focal length itself. So using the same lens, converging with a 6 centimeter focal length. So 6 centimeters, 6 centimeters. But now let's put the object closer. Let's say we put the object much closer to the lens. So it's only, let's say, maybe 2 centimeters from the lens. So we've got the object distance is only 2 centimeters. Focal length is still 6 centimeters. Now if we try drawing out the exact same principal rays, we've got one straight through the center, of course. It just keeps going straight. We've got one that starts parallel and bends towards the far focal point. And also, what's our usual third principal ray here? Can we just draw one from the object towards the near focal point? That's never going to hit the lens, right? but we can draw it in the exact opposite direction. So if you like put a straight edge between the object and the focal point, but draw the ray of light in the other direction towards the lens, that ray is still collinear with the focal point, even though it never actually passed through it. So this still counts as a ray of light collinear with the near focal point. So that's still going to bend to become parallel to the optical axis. Only problem is if you as an observer are standing over here, these rays of light never meet on this side. So we don't get an image over here. But from your perspective as the observer, these rays of light are spreading out. So they seem to have come from somewhere further back here. You can geometrically backtrace these rays. You can trace back to figure out where they seem to have come from. And in fact, that's exactly what your eyes do, or not your eyes, but your brain connected to your eyes does. If you imagine where could these rays of light have come from, ignoring what happened before it hits the lens, these rays of light could have come from back here. So if you backtrace each one, ignoring what happened before, backtrace, 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 these rays of light all seem to have come from this location. So this location is the image based on this object in this lens. Notice that that's behind the lens, right side up, larger than the object itself. And also, since the rays of light never actually pass through this point, what do we call this image? It's not a real image because even though the rays of light seem to have come from this point, so we do call this an image. But since the rays of light never actually crossed that point, we call this a virtual image. The image is just the point that the final rays of light seem to be coming from. If the rays of light actually did pass through that point, we call it a real image. If the rays of light never actually met at this point and we had to backtrace to find it, we call it a virtual image. And in general, the real image is always going to be on the side light is traveling on. So that's going to be a positive value for I. And it's always going to be upside down, inverted compared to the original object. Real or virtual image, on the other hand, is always on the opposite side from the side light is traveling on at the end. You might say it's behind the lens. And it's going to be right side up. It's not inverted. And in this case, it's larger than the original object because it's further away from the lens than the original object. Those are going to be proportional. The distance between the lens versus the height of the object and the distance from the lens to the image and the height of the image. Those are going to be the same ratio because of similar triangles. But there's our virtual image as a result of backtracing. And try applying the thin lens equation to these numbers as well. Exact same equation, but use same 6 centimeters for focal length, but now try using 2 centimeters for the object. Try running the equation on that, see what you get for the image distance, and does that match up with what we get from the diagram. So try that out, try getting some practice with other situations, just make up some focal length for the lens and put an object somewhere, try the ray tracing, and try the thin lens equation, see if the results match up. And see if you can apply the same principle to diverging lenses as well with a negative focal length. So give that a try, get some more practice, and we will look at some more examples next time. You're welcome.